What if the Titanic had today's chemistry to back it up? That question sparked an idea. Ships that can respond automatically to damage or fire, no electronics, no crew input, just materials that react instantly to danger. That's where self activating gel systems come in. These systems are built right into the ship, ready to act the moment they're exposed to seawater or high heat. The science behind them isn't speculative, it's proven, simple, and incredibly powerful. This isn't about replacing the crew or existing safety gear. It's about giving ships a fighting chance when everything else fails. First layer, saltwater activated gel. The first and most critical layer sits just behind the outer hull. It's a saltwater activated gel designed to expand rapidly when it detects seawater, a clear signal of hull compromise. No sensors or software needed, just salt ions. As soon as it gets wet, it swells up to 30 to 50 times its original size, pushing outward into any opening. This sudden expansion creates a dense, buoyant plug that slows flooding and buys time. The material uses sodium polyacrylate, a superabsorbent polymer, as its core. Calcium sulfate helps harden the structure. Expanded perlite makes it float and stay porous. Biodegradable fibers like cellulose or chitosan strengthen it, while boric acid adds fire resistance. To keep it working in low salt water, salt granules are already mixed in. Second layer, thermally activated fire gel. The second layer is a fire suppressant gel, placed in areas at high risk for fire, such as engine rooms or power conduits. This gel expands when exposed to heat, up to 20 times its original volume, and begins to suppress the fire. The gel releases water vapor and carbon dioxide as it grows, displacing oxygen and absorbing heat, thus smothering the flames. It forms a hardened char, acting as a barrier that stops fire from spreading. The key ingredient is ammonium polyphosphate, which forms an intumescent char layer, while sodium polyacrylate aids in thermal absorption. Aluminum hydroxide releases moisture when heated. Silica aerogel and vermiculite add insulation, while xanthan gum stabilizes the gel. Sodium bicarbonate releases CO2 to help quench fires. Third layer hybrid gel. The third layer is versatile, acting as both a fire and water barrier. Positioned between the hull and interior, it can be activated by either saltwater or heat. It expands when triggered by either, hardening into a strong, buoyant, fire-resistant filler. It's designed to deal with both flooding and fires that could occur simultaneously. Sodium polyacrylate again assists in expansion, while calcium silicate provides structural integrity and flame resistance. Expanded glass microspheres help with flotation and insulation. Starch-modified clay and lignin are included for environmental compatibility, while borax and ammonium polyphosphate help with flame resistance and structural stability. The role of gel systems. These gel systems aren't meant to replace the crew or the ship's active systems. They're designed to augment them, acting as a passive safety measure. The beauty of these systems is that they work automatically, with no need for human input. The ship can start reacting to the danger before the crew even notices. In cases of hull damage or fire, these gels can activate and contain the situation, buying time for further action. They're silent, simple, and effective. Economic feasibility. While the implementation of gel-based safety systems may seem costly at first glance, the price is surprisingly manageable. For a ship the size of a very large crude carrier, VLCC, the outer hull gel systems would cost between $500,000 and $700,000, depending on the vessel's surface area. Interior fire control gel installations would add about $150,000 to $200,000. The hybrid mid-layer system could cost an additional $250,000, depending on the ship's design. When compared to the cost of cargo loss, environmental damage, or human lives, these costs are relatively small. Why this technology works. The beauty of this technology lies in its simplicity. The chemistry is already well understood, and the materials are commercially available. The gels react predictably to their environment with no need for external control. What's new is the concept of embedding these reactions directly into the ship's structure, allowing it to react autonomously. This passive safety could radically change the way we think about maritime risk, offering not just protection, but valuable time during a crisis. Conclusion. In an era where maritime dangers, whether from storms, accidents, or onboard fires, are increasingly complex, this passive survivability technology offers hope. The gel-based systems could redefine what it means to sail safely, making ships more resilient when conventional systems fail. Ultimately, It seems we've covered the full document already.